Howdy. Alright, so today we're going to talk about acids and bases, and we're first going to start with some of the definitions and then how they react in the three different types of acids and bases, acid-base reactions, and then we're going to do the NIEs with each of these reactions and some of the exceptions that go along with this. Alright, so you should remember these three definitions: the Arrhenius acid and base, Bronsted-Lowry acid and base, and Lewis acid and base. Arrhenius was the scientist who defined how acids or bases reacted in aqueous solution. So silly, but remember aqueous Arrhenius, aqueous Arrhenius. Okay, so acids are going to produce H pluses in aqueous solution, and bases are going to produce OH minus. This is probably the most simplistic definition here of how acids and bases react. Bronsted-Lowry went a little further, and they actually talked about what was occurring with the proton. Okay, when I say proton, I mean H plus, because essentially that's the hydrogen ion, which has had an electron removed, meaning the only thing left is essentially in the nucleus is simply a proton, which is why we call an H plus a proton. It's easy. Okay, this is the most common for us, and I remember this. I taught this little silly way to myself back in like 10th grade. So an acid here is a donor of a proton, and I call them bad acids because I can remember Bronsted acid is a donor. Okay, so just don't say it really fast. So Bronsted acid is a donor, and then the opposite this is stupid, but it makes it work. It works for me. BBA, Bronsted base is an acceptor. So we're just talking about how the protons or the H pluses are being moved around within a chemical reaction. Lewis acid and bases are ones we briefly talked about in honors chemistry, but it really pertains to the lone pair that's existing. So if something like let's see, ammonia, if you draw out its Lewis dot structure here, you'll see that ammonia has a lone pair on the top, and if that's reacting with boron trifluoride, this looks lovely here. Okay, so if this is reacting, this lone pair is going to now be shared between the boron and the nitrogen here, and it's going to make something like this as it's attached to one another now because of this shared lone pair in the middle. So Lewis acids and bases are actually talking about what happens with the lone pair, and the one with the lone pair, that would be the base, and the one that accepts the lone pair would be the acid. So acid is an acceptor here, and the base is a donor here. And this is different than the Bronsted-Lowry because we're talking about a different chemical, a different subatomic particle. So we've got electrons here working where we have protons or H pluses working in the Bronsted-Lowry. So they're very different. So this is kind of a reaction. We call it a coordination complex, and we're going to actually make coordination complexes in labs this coming week. So you'll actually learn a little bit more about that. All right, so that's just exactly what I told you. We're going to talk about redox reactions, electron transfers later. In redox reactions, we'll kind of revert back to Lewis acid-base reactions as well. So the word conjugate, whenever I ask about conjugate acid and bases, I'm usually referring to the most common acid and bases we talk about, which are the Bronsted-Lowry ones. So a conjugate acid is what's happened, the species that's formed after the base has accepted the H plus. So it's called a conjugate acid because if we reverse that process, that H plus could then be donated, and if we remember bad acid, then the acid is the donor. So it's a conjugate because of the reverse reaction, it does actually act as the acid. So in this case, ammonia, after it's gained an H plus, is ammonium. Fluoride ion, after it's gained an H plus, is HF. And H2O, after it's gained an H plus, is hydronium. So each of these are now called the conjugate acids of these bases. Opposite of that are conjugate bases. They're what's left after the acid has already donated its own H plus. So after HCl donates its H plus, the only thing left is Cl minus. After acetic acid donates its only H plus is C2H3O2 1 minus. This one's different because there are two H's here. Only one depronation or one H is going to be leaving us with HS 1 minus. But if we take that conjugate base here, which is just this one right here we just made, and we deprotonated one more time, then we actually have the sulfide ion left over. So those conjugates are conjugate bases because they have the ability now to actually accept a proton, which is the definition of a Bronsted-Lowry base. Okay, the term amphoteric is going to be kind of like ambidextrous for your left-handed, right-handed. Amphoteric is referring to the fact that you can act as an acid or a base. That means you have to have a hydrogen to donate or a negative charge that you can accept that H plus because opposites attract here. So in this case, this can either make H2S or deprotonate to make S2 minus. So this is amphoteric. Most of our diprotic acids will be amphoteric. This has the ability to make H2SO4 by gaining, or make SO4 2 minus by losing another proton. Water can become OH minus, or H3O plus, which is hydronium. This is hydroxide. And then this last one can either become H3PO4 or HPO4 2 minus, or PO3. PO4 3 minus. So this one's got a lot of possibilities. And just so we all are clear, the name of this is dihydrogen phosphate. So know that name. This is just simply telling you there are two hydrogens attached to the phosphate. This is different than biphosphate, because the bi in the front of phosphate just means there's one hydrogen there. So don't mix up bi and di here. Okay, as we go down, this one right here is called, you guessed it, monohydrogen phosphate. Alright, so you'll see some terms like that. Don't get confused. The mono means there's one hydrogen, the di means there's two hydrogens. Alright, so here's our first reaction, an acid-base reaction is neutralization. It's just a double replacement reaction, but we're actually reacting an acid and a base. And so if I call this, let's say H is always with acid, so it's nice to put H there. X, so we've got a binary acid here reacting with Y, OH, because bases usually have an OH. There's some other bases, but we'll talk about those later. And then the H is going to recombine with the anion, which is OH here. So HOH is water, and that's usually going to be our liquid. And we do not ionize liquids, pure liquids, because they are pure. They're not ionizable. The salt is going to be the cation, which is Y, and the anion, which is X. Just make sure you put that in order whenever you write it out. If it looks funny, it's probably wrong, so use your common sense. Okay, so this is just a double replacement reaction. That's it. Most of the time, the salt is going to be aqueous, as well are the acids and the bases. You've already written down the definitions here. This is just a quick reminder. Salt is not just NaCl. Salt is anything. K3PO4. Any ionic compound is called a salt. Anything. So this is just referring back to the Bronsted-Lowry and Bronsted bases, or Bronsted-Lowry acids and Bronsted-Lowry bases. Remembering that the acid is going to be forming the conjugate base after it's lost its H or donated its H, and the base is going to be forming the conjugate acid. So if I ever ask you for a pair, an acid and conjugate base pair, I'm talking about those two, or a base and a conjugate acid pair, I'm talking about the middle two. So just, be wary of that. Don't just keep writing and think the acid goes with the acid. Okay, so that's why I said they occur in pairs. The stronger the Bronsted-Lowry acid, the weaker its conjugate base, because if it's an acid and it's strong, it really wants to get rid of that H+, so it makes the conjugate base weaker because it has no desire to gain it back. Okay, same thing with base. The stronger the base, the weaker its conjugate acid, for the same reasoning. We've already written this down. There's just some pictures that go with this. So this is going to be the acidic H that's being donated. So obviously here we have our acid and we have our base. And after it's donated, we now call this the conjugate acid, and this is the conjugate base. Okay, so whatever is the result of the acid, there we go, acid losing its H is the conjugate base, and opposite for the other one. And this is just a little more detailed where you can see the different elements and their electrons and their charges. Alright, the last reaction we'll talk about is hydrolysis, hydrolysis. Hydro means water, lysis means to break apart or split. Okay, so water is doing the breaking apart. So water is going to kind of take this salt and divide it and do the double replacement reaction with that. So in this case, we have cation, anion. Well, let's do it the way I did it earlier. Okay, YX plus HOH yields This is going to be a H plus that's going to bond with the anion here, which is HX in this case. And then this OH is going to bond with the cation in this case, which is YOH. And that's exactly what I had for neutralization, except backwards. So if you remember, neutralization and hydrolysis are just opposite. You are going to be in awesome shape. Alright, so let's do some examples where we actually want to write out the NIEs with this. So write these down with me. HCl plus magnesium hydroxide yields HOH, which is a liquid, and MCl2. Okay, so that 2 there for hydroxide means I need a 2 there. That 2 for chlorine means I need a 2 here. Alright, now we're balanced. If I don't tell you something is a solid or liquid, then you're going to assume aqueous. Do you remember that from last lecture? And we all know that this magnesium chloride is also aqueous because halides are soluble. Water is liquid here, though. We do not break apart water. Let's go ahead and do that with the whole problem. You'll see why. So there's 2 H's here. So it's 2H plus. That 2 also means there's 2 chlorines plus 2 chloride ions plus Mg, 2 plus 2 OH minus yields 2 waters. I'm going to write H2O for your benefit there. And an Mg plus, 2 plus, and 2 chloride ions because of the subscript 2. Once you go through and you cancel out your spectator ions, you'll see that magnesium, 2 plus goes away, 2 chlorines go away, leaving us with 2H2 plus 2OH yielding 2H2O. Is that the final answer? No, we need to reduce this down for 1 H plus, 1 OH minus, and an H2O. And that's because the VCE needs to be in the lowest coefficients across the board here. And if you want to keep that labeled liquid so that you don't forget that there's a reason, there's a reason you didn't cancel that out. Okay, so that's our final answer. That's our NIE for this reaction. Any acid and base reaction, a lot of times if it's strong acid and base, then you'll have this NIE. Alright, this one's special. So if you look at the little footnote down here, the first proton in sulfuric acid is ionized completely, and the second is only partially ionized. This is the only polyprotic acid that exhibits this property. That's because sulfuric acid, if you remember, is a strong acid. Okay, all other polyprotic acids are weak acids written in the molecular form. This is how we want to write this out, okay, whenever we ionize it. Okay, so first of all, let's start off the BCE like normal. HOH, so water, and sodium sulfate. Okay, the 2 there means I need a 2 here, and we good, 2, 2, 2. Okay, so for the molecular kind of equation, the total ionic equation, this H, one of them pops off because it's a strong acid, but it's only strong for the first ionization, plus H, SO4, 1 minus, plus 2 sodium ions, okay, because that's going to be ionizable, plus 2 OH ions, okay, because we're just pretty much splitting that in half, yields 2 waters, which is a liquid, don't forget, 2 Na pluses, because this is soluble. I didn't write this down, but you need to probably, so you remember what's soluble and what's not ionizable, what's insoluble. Alright, so plus 2 sodiums and a sulfate. Alright, so as you go through here, you're going to see that you can cancel your sodiums. You can cancel your sulfate? No. This sulfate has an H with it, therefore they're not identical, meaning you cannot cancel out that one. The only spectator here is sodium plus. So our final NIE would be H plus H2SO4 plus 2 OHs, yielding 2 waters plus a sulfate. Okay, so you'll see it this way. You'll also see it the other way. It depends on if it's going to completion, if the reaction is entirely allowing for all of the H pluses to react. And if that is happening, it'll probably say to completion. Okay, it doesn't indicate that here, and you've never seen this before, so this is a good way to kind of remember to do this. Alright, so now we have a hydrolysis reaction. How do I know it? Because I've got H2O as a reactant. So if ammonia is going through hydrolysis, this is what's going to be occurring, because essentially it makes ammonium hydroxide, but ammonium hydroxide is very unstable, if you remember that from the last lecture, and therefore it actually ionizes in solution to make NH4 plus and OH minus. Okay, if I just want you to label this as conjugate acid and conjugate base and acid and base. First of all, you'll see that the H2O donated NH to NH3. That's how I got the extra H plus here. So if it's a donor, it's an acid, meaning this has to be the base because it's the acceptor. And then if you follow through the products, the base makes the conjugate acid and the acid makes the conjugate base. Down here, we've got H2O and we've got a nitric acid. I know this is nitric acid, but I want to double check that it's actually acting as the strong acid here, the one that's predominant. I see that the H is being donated to the H2O because that's how we got the H3O plus. So if you're the donor, you're an acid. If you're the acceptor, you're the base. Whatever you made is the conjugate base, and whatever you made base is the conjugate acid. What you'll notice here is between the two reactions, water is acting amphoterically. Okay, that means it acts as an acid in one and a base in another, and water does that, and also ammonia does that, which you'll see on the next slide. But if I want you to predict the end solution pHs, if it's acidic, basic, or neutral, you can do that by looking at the species present. The OH is present here, meaning this last bit's going to be basic. Okay, the H3O plus is here, means that the final solution is going to be acidic. Okay, it depends on the predominant species in the end. And OHs always cause something to be basic, and hydroniums always allow something to be acidic. This table, there's tons of variations of these, but this table indicates to you the relative strengths of acids and bases. You should recognize these 6 ones at the top as being our strong acids. So we have perchloric acid, which is not named there, hydroiodic acid, hydrobromic acid, hydrochloric acid, nitric acid, and sulfuric acid. So these are our 6 strong acids. And then their Ka values, which if you didn't learn about that in honors chemistry, this value, if it's greater than 1, just indicates to you that's a strong acid. Okay, if it's greater than 1. It's a really tiny number, so these are tiny numbers here. These Ka values are really, really small, and as you keep going down further, they keep getting smaller. Therefore, these are all weak acids. Okay, so you can see the labels here, weak acid to strong acid, and then weak base to strong base. So if you look down here, you'll recognize some of these as being somewhat basic. Okay. This is another picture indicating to you why we label something as a strong acid versus a weak acid, because strong acids have 100% dissociation or ionization. We kind of use those words interchangeably here, even though we all know that you're not supposed to. So 100% ionization dissociation means that all of this HA does ionize to the 2 ions that make up that molecular compound. There's no HA left at all. 100% of it dissociates and changes from the dual form here to the ionic form here. Okay. Over here we have a weak acid, so there's a very little ionization, meaning that there's HB, and as the HB ionizes, it makes H pluses and B minuses. But there's such a small portion here compared to the original HB that initially was present. You'll see here in the picture form, you've got 1 ion here and 1 ion here compared to all of the other original form that never actually ionized. So remember the definition and what the pictures look like, because you will be asked to draw that on my test. Amphoteric or amphoterism here, I've already told you this, but you've got the waters that act amphoterically. Waters can auto-ionize with each other. Water can donate NH here to make hydronium, and once it's lost that H plus, it's a hydroxide. And this is important because this happens all the time, okay, in water. All the time. I don't know what that says. All the time in water. And if you remember the Kw constant, which is this number right here, 1.00 times 10 to the negative 14th, the reason we know this number is because the concentration of hydroniums times the concentration of OHs whenever you just have water present at 25 degrees C. So it's very specific at the temperature at which it exists. It might vary with the concentrations here, but when you multiply them, it's called the ion product constant. When you multiply those concentrations, it's always going to be this number. Always, always, always. Whenever it's neutral, the reason we know it's neutral is because if they're equal here, you've got equal concentrations of both hydronium and hydroxide, which is each of them being 10 to the negative 7th. We'll use this when we do pH calculations on the next lecture. Ammonia and ammonium kind of do the same thing. We got ammonia and then, ammonia donates to make ammonium cation, and it's amine, which we don't see often, but if one's got the H plus, the other one has H2 minus. Okay, so we're going to start writing reactions out a little bit. I've got a couple of examples to do with you. These are all kind of beware and notes that you need to know, okay? Usually you're going to look at the acid and base, and sometimes it may not be explicitly a strong acid and strong base. You're going to have to figure out which is acting as the best acid and which is acting as the best base. So usually Bronsted-Lowry will apply here. You're going to want to see who's going to donate and who's going to accept. And this is just going to tell you that a strong acid or weak base, or strong acid or strong base will yield a weak acid or weaker base. This part here, decomposition of unstable products, would be something like in our lab where we have a carbonic acid forming water and CO2, because this carbonic acid is very unstable and it actually automatically converts to these products. Another version of this is with H2SO3 yielding water and sulfur dioxide. So sometimes this happens and you do need to fulfill the final second reaction that's occurring to this more stable products. Another term you'll see is equimolar, and equimolar just means equal moles. And if you have a dicritic acid present in a base, then you can actually react, but only react with one of the H's present. So not all H's will neutralize, which is related back to our H2SO4 example from earlier, where just one of the H pluses were pulled off and pulled into the water. This monobasic, dibasic, tribasic compounds, that's referring to how many H pluses have been neutralized in the reaction. So for example, a product that you could form here would be NaH2PO4, and I will call that monobasic sodium phosphate, because one of the H's from phosphoric acid were ionized. You want a dibasic, then you'd have Na2HPO4, because it says dibasic sodium phosphate means two sodium hydroxides possibly were reacting with phosphoric acid and two H pluses have been neutralized. So the terminology is really specific, you just got to know what it means. Free halogens with dilute bases or OH minuses in solution form hypohalate, or hypohalate ions, hard to say that, but this is very rare. We don't see this too often, but it's beware, it is possible to occur. And then if anything ever says bubbled through solutions, you're going to take that gas, these are three gases, in water to make the unstable product that we actually had initially noted up here at the top. It's opposite here. We're actually going to be forming these, and they could decompose still, but we do want to know that we can actually form them. Alright, I have 10 acid-base prediction problems to do with you. If you want to stop the video and try to do a couple of these by yourself and then look at my solutions, that would be great. Try to challenge yourself with your nomenclature. I'm going to go fast through these. Alright, so we have potassium hydroxide and nitric acid. They're mixed, so we have an acid-base neutralization reaction. This is a strong base, and this is a strong acid. So we have the ability to ionize everything. That's just a note to remember in the end. We get potassium, nitrate, and water. This is balanced. Okay, water is a liquid, pure liquid. We don't ionize that. K plus gets ionized. OH minus plus H plus, because that's a strong acid, plus NO3 1 minus. Yields this salt here is going to be a soluble salt because all nitrates are soluble. So K plus plus NO3 1 minus plus agua. Okay, and that's our liquid form. We don't ionize. So the potassium is present on both sides. The nitrate is present on both sides, leaving us only with OH minus and H plus to make water. And I told you that this would happen a lot with your neutralization reactions, specifically if you have a strong acid and a strong base where the reactants are all ionizable. Okay, and I don't label these aqueous, but we all know they're aqueous. Alright, sodium hydroxide reacts with nitrous acid. So we don't have HNO3, we have HNO2, which is a weak acid. Therefore, we will not be ionizing that in the end. Sodium makes sodium nitrite. and HOH, which is our liquid here. This is ionizable. Na plus plus OH minus because that's a strong base. This is not ionizable because it's a weak acid. Okay, so we leave that intact. The sodium nitrite is soluble because sodium is a group 1 metal. NO2 1 minus forms plus HOH, which I'm going to write as H2O now, liquid. So in the end, the only thing that's a spectator is the sodium plus, leaving us with OH minus plus HNO2, yielding NO2 1 minus and liquid water. Okay, and I'm going to write each of these as aqueous just so we remember these are floating around in solution, and the weak base never actually, or sorry, the weak acid here doesn't really ionize well, so it stays intact. And final answers I like it squared or circled so I can find them easily in your paper. Alright, solutions of hydrofluoric acid. Think to yourself, is that strong or weak? You should be saying weak. And ammonia, NH3. When they react, they actually, it's funny, but they can make NH4F. It's kind of like a synthesis reaction, but this is going to then be aqueous, and all ammonia compounds are soluble, meaning that we have a secondary reaction that occurs that make NH4 plus aqueous and fluoride ion aqueous. Okay, so aqueous all the way around means that this nothing cancels from the reactant side and nothing cancels with the product side, so the full reaction would be these reactants making these products. So no ionization at all. And if you're really thinking about it, would you see any of this forming? Then no. So then I put no reaction here as well, because technically there's no precipitate, there's no gases forming, there's no weak acid or weak bases. Solutions of acetic acid, so HC2, H3O2, and sodium cyanide, NaCN, are mixed. Acetic acid is a weak acid, sodium cyanide is a salt. Okay, so we're going to just do our double replacement reaction here, where we get HCN plus NaC2H3O2, so sodium acetate and cyanic acid, or hydrogen cyanide. This is also a weak acid. So note to self, do not ionize, do not ionize. This is balanced. Yes, this is balanced. So we've got HC2H3O2 plus cyanic acid is ionizable because it's just a salt. That's going to be soluble because of our group 1 metal, making weak acid, which you don't ionize, and a salt that is ionizable because acetates are soluble as well as your group 1 metals. So the only things that are aqueous that are spectator ions is the sodium plus, leaving you with HC2H3O2, so acetic acid, plus the cyanide ion, yielding cyanic acid and acetate ion. And just to be sure, all of these are aqueous. If you were wondering, they're all going to be in solution still. Okie dokie. Next, we have solutions of acetic acid and potassium fluoride. So C2H3O2, so our acid, remembering it's weak, and KF, so that's our potassium fluoride. Same kind of story. We've got HF, so hydrofluoric acid. Remember to yourself that's not strong, even if it does dissolve bodies in Breaking Bad. C2H3O2, so potassium acetate. This is soluble because it's a group 1 metal. Weak acid, do not ionize. This is a soluble salt because it's a group 1 metal. Weak acid, do not ionize. Same story. HC2H3O2 plus, and I'm going to go ahead and look at this now. I know that this K is going to be a spectator because it is ionizing, and this K is going to be a spectator because it ionizes. So I'm jumping to the chase. The fluoride ion remains behind because it's not a spectator ion because it's stuck in the hydrofluoric acid form, and acetate is able to be freed from potassium. So here's our final answer here. Okay, and this is our final answer here. Let's see if I can get this bid. Okay, so all of these are all aqueous as well. Next one's a little different. 1 mole of phosphoric acid is added to a solution containing 2 moles of sodium hydroxide. So they're kind of telling you a little about the stoichiometry here. So phosphoric acid is H3PO4 because you don't see the hydro, so you know it's a polyatomic ion. and sodium hydroxide. Okay, you know that 2 moles of sodium hydroxide can neutralize 2 moles of H pluses. If you have 2 moles of H, you actually have 3 moles of H pluses here, then you know that not all of it's going to be able to be neutralized. Okay, so if 2 of them can be neutralized, you're going to leave 1 of the H's intact with the PO4s. Rewind that if you need to hear that again. Okay, so the sodium is going to be present in solution, and there are OHs, 2 moles of OH is present. That take away 2 moles of the H is present in phosphoric acid, leaving us with HPO4. The charge of that is actually 2 minus, because 2 of the H's got neutralized. So that 2 minus gets crisscrossed down to be Na2HPO4. So sodium dihydrogen phosphate. Alright, and we've got H2O that's forming, but 2 of them are forming because I need to have this balance. 2 OHs are balancing or neutralizing 2 H's, so there's going to be 2 waters formed. And let's just double check, is that balanced? No, I forgot, there we go. And those 1 and 2 came from our initial stoichiometry given to us in number 6 here. Liquid water is formed. Let's talk about this. This is a weak acid, so don't ionize that. That's a strong base. Do ionize that. This is a salt, and I will tell you now it's a group 1A metal, so it's going to be soluble, and this is insoluble. Don't ionize that. Okay, so this weak acid we leave alone, H3PO4 plus 2 NAs plus 2 OHs, yielding a salt that's going to be breaking apart, 2 Na pluses plus HPO4 2 minus, and 2 waters. Only things that are capable of being canceled are the 2 Na pluses on both sides, leaving us with a final answer of H3PO4 plus 2 OHs, yielding HPO4 2 minus plus 2 waters. Okay, and I'm just going to leave that one liquid there. Everything else is aqueous. That's a hard one, so you might want to watch that one again if you don't remember how to do that one. Number 7, gaseous hydrogen chloride. So hydrogen chloride is another name for hydrochloric acid. Sometimes when it's in gaseous form, they don't write it as acid. They just write what the gas is called because it's just a molecule at this point. It's not going to be dissolving in solution. Is bubbled into a solution of sodium bicarbonate, NaHCO3, which is just baking soda. What does this make? Well, the H's comes together with the HCO3 to make carbonic acid, and the NaCl comes together. Okay. This is going to be that unstable product that forms water and CO2, and I'll write that down below again. Alright, this is a strong acid, however, it is gaseous. Be careful. When it says gaseous, you may not ionize it, because we don't have gases just poofing into ions in the air, okay? They stay together. This is going to be a aqueous kind of solution, because it actually says solution of sodium bicarbonate. This is going to be aqueous solution as well as this. So do not ionize the strong acid. Leave it alone. So HCl plus Na plus HCO3, 1 minus, yields water, which is a liquid, plus CO2, which is a gas, plus Na, which is aqueous, plus Cl, which is aqueous. Alright, so the only things that we're capable of canceling is aqueous sodium, and that's it. Leaving us with gaseous hydrogen chloride, even though you want to call it a strong acid, it's not in this case, okay, plus the bicarbonate ion, yielding liquid water, which we leave alone, plus carbon dioxide gas, which we leave alone, and chloride ion, which is aqueous. Alright, so that's a really good one, because you could easily make a mistake on that. Since the states are actually, the substance is bubbled through, you know, you could possibly leave that carbonic acid, but the best answer here is actually to put the decomposed products from the unstable carbonic acid. Alright, so now we're getting picky. Solid copper 2 oxide. So here's copper 2 oxide. It's a solid. Don't ionize it. Is dissolved by hydrochloric acid. Alright, now we have our acid, which is aqueous because it's going to be a solution. Alright, so copper 2 oxide hydrochloric acid made copper 2 chloride and water. So the H comes together with the O, and the copper and the chlorine come together. But we can't have H and O, that's just OH together. It doesn't exist by itself like in this case. So we need to put H2O, meaning, balancing here, we see the 2's over here. That should indicate to you that you need a 2 on the hydrochloric acid. And it actually works itself out. So you could easily make that mistake, but once you balance it, you wouldn't be able to, so you go back and check yourself. Alright, so the solid stays together. That's a solid, plus 2 H pluses, plus 2 chloride ions. Yield, is this soluble? Yes. Okay. All halides are soluble, including the copper, which is a metal, but it's not one of those heavy metals. So copper 2 plus chloride, but there's 2 of them, plus H2O, which is a liquid. Don't mess with it. Alright, the only thing present on both sides are the chlorines. That's it. Copper 2 oxide solid plus 2 H pluses yields copper 2 plus 2 H2O liquid. Okay, that's a really good one too because we've got the solid component there. Don't forget about that. Alright, ammonia gas is bubbled into water. Water is a pure liquid. Do not put aqueous. You can't have water dissolved in water. It's just straight up water. Okay, when you synthesize this together, you get ammonium hydroxide, and we kind of talked about this earlier. This is an unstable product, so I would write NH4 plus OH minus. This would never stay in solution. It would always form the ionic form here. So that's aqueous, and that's aqueous. Okay, so in the end, if we wanted to finalize our NIE, we'd have gaseous ammonia plus water, liquid, yields NH4 plus OH minus. Okay, nothing can be canceled here because there's no spectators on either side. I would write this out, but technically there's nothing to see here. You can't see what's happening. I would write this as no reaction, just maybe in the end, just to show them that you do know what you're talking about. On the AP exam, though, they should not give you no reaction because they want to see your chemistry knowledge, not the fact that you can just tell me there's no reaction. They want to know a little bit more. Last one, solid potassium hydride. So remember, hydride is just hydrogen with a 1 minus charge. That's H1 minus. So potassium and hydrogen is potassium hydride. And it's solid. Don't forget to label that so you don't forget. Is added to water. That's liquid. Making, all right, the H, and I'm going to rewrite this as KH plus HOH, can come together. So that's KOH. And then these two hydrogens come together, which is H2. So that's hydrogen gas. Okay, this is a gas. This is aqueous. So when we rewrite this, we can write this as KH solid because it does not decompose, it doesn't ionize. H2O liquid because it doesn't decompose, plus K plus OH minus plus H2 gas. You'll notice that nothing is able to cancel because everything is going to be, there's nothing present on both the reactant and the product side. So you leave it as it is. That's it. And you can even write, for instead of gas, you can put an arrow up if you like that instead. Alright, if there's any questions on acid-base reactions and NIEs or some of the terminology that I've talked about today, let me know. But we'll start the other stuff tomorrow. Alright, thank you very much.